Okay, let's start off with some of the fundamental definitions of what is discrete probability theory. Let's let omega be a countable set, and here note it's a capital omega. Assume that p is a function from omega to the reals that has two properties. At every point in omega, the function p of omega is between 0 and 1, and the sum over all points of omega of p omega is 1. Capital omega is called the sample space or the outcome space, and each individual little omega is called an outcome. Any subset of omega, let's say E, is called an event. So an event is a set of outcomes. We define the probability of the event E to be the sum over all omega in E of little p of omega. Okay, here's an example. Let's say we roll one 6-sided fair die. If we roll a 6-sided die, the set of outcomes is the set 1, 2, 3, 4, 5, 6. Saying that the die is fair means that all of the outcomes have equal probability, but also notice that all of the outcomes must add up to 1 by assumption. Therefore, 6 times p of 1, say, is 1, and therefore p of 1 is 1/6. And in particular, p of any of the omegas is 1/6. So for example, one event is roll a 5. That's the set consisting of the single outcome 5. The probability of that set is just p of 5, which is 1/6. Another event is roll an even number. Well, that's the set 2, 4, 6. So we have to compute p of 2 plus p of 4 plus p of 6, which is 3/6, or 1/2. Okay, now we're going to define what's called a random variable, or in this context, specifically a discrete random variable. Let's let capital X be a function from omega to the reals. It can basically be any function we like. Notice since omega is countable, the range of X is also countable. For any k in the range of X, in other words, any value k that X can take, we define the probability that X equals k is the sum over all omega such that X of omega equals k of p of omega. Then we define the probability distribution of the random variable X is to be the collection of all these probabilities in order. Okay, another example. Let's say we roll 2 dice. Let's think about all the outcomes that could happen. Notice that the first die can be any number from 1 to 6. The second die can be any number from 1 to 6. So we can record the outcomes as the ordered pair ij, where I and j each range from 1 to 6. Let's write out all possibilities here. Omega is going to be the set of all such possibilities, and we can see that there are 36 possible outcomes. Now let's pick a random variable to be the first die minus the second die. We can then, for every point in the outcome space, or specifically for every outcome, we can evaluate x of little omega, and we can write it in this same array, and we can see all the possible values that x can take. And now this allows us to compute probabilities. For example, the probability that x equals -3, well, there are 3 outcomes that give us a -3. Therefore, the probability is 3 over 36, which is 1/12. Similarly, the probability that x equals 2, notice there are 4 outcomes that give us the value 2. Therefore, the probability is 4 over 36, which is 1/9. Okay, one last example. Let's do the following. Let's start flipping a coin, and we keep flipping it until we get the first heads. Then let us count the total number of flips, and let's say the random variable x is that number of flips. We're going to make an assumption here that any given sequence of flips of length n has probability 1 over 2 to the n, which is just saying that all sequences are equally likely. Then we compute. What's the probability that x equals 1? Well, that's the probability of getting ahead on the first toss, which is 1/2. The probability x equals 2 is the probability of the sequence tail head, which is 1/4. Notice the first one must be a tail if x equals 2, because if the first one were a head, then x would have been equal to 1. Similarly, the probability that x equals 3 is the probability of the sequence tail head. The first 2 had to be tails if x equals 3, because that meant that the third roll was the first head. We can see the pattern here. The probability that x equals n is 1 over 2 to the n. Let's just double check to make sure we're on the right page and notice that if we add up for all n equals 1 to infinity, the probability x equals n, well, that's the probability n equals 1 to infinity of 1 over 2 to the n. Using the rule for geometric series, that gives us 1/2 over 1 minus 1/2, which of course is 1. Notice what's interesting here. X takes on infinitely many values. X can be any natural number. So it's not finite, but it is countable. Okay, and then we can compute all kinds of events. For example, the event that x is less than or equal to 3 is the probability that x equals 1, or the probability that equals to 2, or the probability that equals to 3, and that's 1/2 plus 1/4 plus 1/8, which is 7/8. Here's a more interesting calculation. How do we compute the probability that x is even? Well, again, that's the probability of the set 2, 4, 6, 8, and so forth. Or we can write that as the sum over k even, the probability x equals k. Writing k equals 2l, where l is a natural number, gives us the sum, l equals 1 to infinity, the probability x equals 2l. Plugging in the formula, that gives us 1 over 2 to the 2l. Knowing that 2 to the 2l is 4 to the l, this gives us the geometric series with ratio 1/4, which actually sums to 1/3. That's interesting. So, of course, the probability that x is odd, we could pretty much deduce from this, is going to be 2/3. So notice that odd numbers are twice as likely to happen as even numbers. Think about why that might make sense.